Differentiation in physics. We have a differential operator, D. Sometimes we use this notation. This indicates the total derivative, and this indicates the partial derivative. If a function is depending on a single variable, this is identical to this. However, if a function depends on two variables, this one is using chain rule. So the difference between this round shape operator and the operator, difference appears when the argument is a single or double or multiple variables. So remember this. Operator this D originates from Leibniz. Newton and Leibniz developed differential operator. Newton did not introduce the differential operator. He used the primes. Single derivative is a prime. Double prime means double derivatives, and so on. Leibniz's way is much easier to write and easier to deal with algebraically. So we prefer Leibniz method to Newton's method. But in some case, something like this, we use Newton's method. So in this class, we focus on a single variable function. Consider time derivatives of position operator. We assume that position of a particle depends on time. So this is a vector and that has a single variable. Time derivative definition, single variable function's derivative is the slope, limit of a slope. Function at t plus delta t, the difference in the horizontal axis and difference in the functional value and the ratio, that is the slope. So delta x over delta t as this denominator approaches 0, then this is a finite case. If you fix a point t, then this point is fixed and it reaches a tangent. When it reaches a tangent, the curve and this straight line passing the point, they meet only at a single point. Okay. In some case, we have a function, continuous, but it has two different slopes. So slope on the left and right can be different. In physics, you can generate a wave along a rope, and if you oscillate this left part and it generates a wave, it may propagate. However, if a string has different density, is a heavy and is a light, in that case, this kind of kink can appear physically. So even in the wave propagation, if the medium has a significant difference at a boundary point, a function representing a wave could make a kink. So you should allow that the derivative on the left and on the right could be different in some case. So in that case, you have to distinguish whether this zero is a positive or negative. So in some case, we use a special notation, a zero plus, that is epsilon goes to zero, but epsilon is a positive. So in this case, if you attach a plus here, then you are looking at the right side of t. So delta t is positive. If you're looking at the left part, then you had better to write delta t goes to 0 minus, and 0 minus is epsilon goes to 0. However, epsilon is negative. For example, if you throw a ball on the wall at t equals 0, it hits the wall and bounces back. What is the velocity? Yes, you can compute the velocity. However, at t equals 0 minus, velocity is a positive. But right after hitting the wall, so t equals 0 plus, it bounces back. So in this case, the function has discontinuity. The velocity, slope, okay, something like that. Slope on the left of t equals 0 is a positive, and then slope after hitting the wall, it is negative. Okay, this kind of situation may happen in physical situation. Numerator is differential displacement. Okay, change in displacement. Linear momentum is defined by, okay, linear momentum is a mass multiplied by velocity. So it is a scalar. It is a vector. Find the physical quantity that is linearly dependent upon P. Yes, P, x dot, they are linearly x vector dot. So they are linearly dependent. Remember, here, this x dot derivative, this is difference. But x dot at x, this is a scalar. So why don't we, to simplify this analysis, why don't we consider this? We have three vectors. If you have three vectors, you can construct a triangle in general, right? Three vectors, they are linearly dependent. So this is position at t, this is position at t plus delta t, and this is vt delta t, something like that, displacement. So this one and this one does not have to be linearly dependent. In one dimension, it is possible to have velocity and position. They are linearly dependent. However, from 2 dimensions or higher, it is not linearly dependent. It is not linearly dependent. So they can be, in general, linearly independent. So why don't we consider f's derivative is g? Then we would say they are equivalent. This is a definite integral. Here, g, if I substitute this one, a2x what is the primitive function of this? This is f of x and subtracted by f of a. Sure, there is some arbitrary constant can be added to this primitive function or indefinite integral. They always cancel in the upper limit and lower limit. So this value is uniquely defined. So g is a derivative, the derivative of f. This is exactly equivalent to the g's integral from a to x plus f of a is in general f of x. You learned in high school. We use this one to find some integral. Find the similar relationship between x and x dot. X dot is defined by the time derivative. Okay, so using this one, velocity's integral integrated over the interval should be the difference of the position, right? Difference of this f. So evaluated t and t0. So if you write any kind of derivative, you can always write down equivalent equation. So derivative can be written in the integral form. Always, they are equivalent. You have to remember. So why don't we move this one to the left and exchange the left and right? Then if you know the initial, it is called initial position. So initial condition, for example. This is a first order derivative. If you compute this x, then you have a single free variable that is a vector. The position at t equals 0 should be known to determine the position of a particle at any time. And the difference, that is the displacement, is the integral of the velocity with respect to time. Double derivative. Acceleration is the time derivative of velocity. Therefore, it is double time derivative of position. Okay? Using this method, I do integrate over time only once, then this double derivative becomes a single derivative, and this definite integral is always the difference. Okay, so using the similar method, I move this one and exchange the left and right. Therefore, I can determine the velocity completely when I know the initial value. And then we can integrate this equation one more time. Then, using similar method, this one is replaced with after integration and the difference. So this one has been moved from left to the right. And then this dot should be integrated over. we remember this and substitute this one in here, and we have this one is replaced with this. So this guy is this, and this guy is this. So we have constant term that is the position at t equals 0, and this is the initial condition for the velocity that is constant vector that can always be factored out. So we are left with the trivial integral. That integral is this. And then innermost contribution is the time-dependent contribution that cannot be factored out. We have no choice but to integrate the whole thing. 0 to 1 dt, what's that? This is a t sub 1, 0, is it? 1 minus 0, something like that. So prime t, then it becomes prime and t minus 0. What happens if I have t dt prime to t? Oh, in that case, it is 1/2 t prime squared 0 to t. So it is 1/2 t squared. Therefore, this integral is just if this one is a constant acceleration in case, for example, free falling motion. If it is constant, this integral is proportional to 1/2 t squared. Sure, if you consider t0, then 1/2 t minus t0 squared.